Alrighty, hello everyone. What is happening? Hello Tutu and Xluxy, welcome back. It's been a while, hasn't it? Once again. Let's get my graphic out of the way. And let's make sure that I have my audio settings the way I kind of want them. You would think that I could like do these things beforehand so that I would have everything set up when I start streaming. And you might be correct. But regardless. Can you guys hear me all right? I can hear you loud and clear. Thanks for the report. It's been like 2 weeks or so. It's been more than 2 weeks actually. It's been more than 2 weeks because I have been kind of away from. Well, I haven't been away from the Madrigal stuff for 2 weeks, but I've been working for my other job for a couple of weeks, and that means that I haven't really had any chance to do any sort of streaming or anything like that. And I think the last stream that I did was the first person mod stream, which was almost a month ago. So maybe they'll lower the music. Let's do that. Let's do that a little bit. Alright. Maybe that's better. Do let me know if the situation changes here. But yeah, I've been very busy. I've been very busy. The fact that I haven't really done a whole lot on stream or video or on Discord for that matter doesn't mean that I haven't been busy. I've been actually super busy. With all kinds of things. Just all kinds of things. Both Madrigal and non-Madrigal related things. I spoke a little bit about some of this stuff on Discord actually. See, can we build the game here? And actually get it running. I had to do a little bit of a rebranding almost. All of a sudden. Completely my own fault, one might say. Well, mostly my own fault. Because I had used some fonts that turned out I wasn't actually sure I could use in the end. Yeah, let's put down the music of the game here. You can see that this font in the logo is slightly different. You can also see that this font used in the actual texts of the game is slightly different. Turned out that the licensing for the two fonts that I was using for this wasn't quite as clear cut as I had thought. So I had to do like an involuntary deep dive into font licensing, and I even did a little bit of font, shall we say, redesign, because I've taken two fonts that I know I can use because they're licensed under the open font license, but I've actually changed them quite a bit, so I've actually done like actual like font design for this game now. Anyway, we now have two fonts that we can use, and I think they look pretty good. But that also means that like if some of these fonts now actually kind of don't look good in some scenario, I can actually just go in and change that because I have the source files for the fonts and everything. The kind of stuff that you wouldn't really sort of think you would do. And while at it, I actually went in and just like switched out the font for the ImGUI stuff as well. So now we have just like all fonts that we can actually ship the game with. This was like a completely unplanned for thing that just kind of happened upon me all of a sudden. And so it set me back probably like not quite 2 weeks, but like 1 week of evenings of just working on this stuff, because like as I said, I've been working for my other employer. So fonts in design cannot be licensed, only in implementation. Yeah, that. Yes, you are correct. You are correct. However, it's not always quite as simple as that, shall we say. I've done quite a bit of research into this, and it seems that some people have only gotten away with using a font if they've actually like retraced every single character and things like that. And I just figured like, I can't be bothered with that, so I'm just not gonna do that. To be clear here, I could have probably licensed those fonts, but the text, the sort of explanation for how to do that was kind of vague enough that I was just like, I don't want to go there. And I was kind of prepared for it to be somewhat expensive to begin with, but this like game game licensing for the fonts that I wanted to use didn't even come with like a price tag. It was sort of like a contact us sort of deal, and I was like, nah, I'm not gonna do that. Another thing that I of course do is that I actually embed the TTF files in the game itself. It's just the easiest way. I don't have to do that. I could ship it in another format, which I kind of started looking into a little bit, but then decided, nah, I'm just not gonna use a font that I can't actually embed here. So now I can actually, I can ship these fonts, implementation and all, as long as I adhere to the open font license. So that's pretty nice. Right, we have a lot of messages. Let's see. Blah blah blah. Game engine devs and OS devs are almost the same crowd, I've noticed. Okay. Maybe that is true. I don't really know any OS developers. I have a question I wanted to ask you, like in the last stream. I'm currently working on shader compilation stuff, so I can reload shaders on the fly. I'm kind of curious how you create your pipeline layouts. Okay. Sure, I can show you that. I can show you that before we actually get going with today's stuff. So let's go into. We're gonna juggle like 2 Visual Studios and probably like 2 Visual Studio codes today. So like 4 different IDEs. It's just crazy town today with the work that I'm doing currently. Shut all of this down at least. Yeah, I haven't even gotten to talk about what we're gonna do today, but it's all good. It's all good. So let's take something simple like screen fade, for example. Screen fade is a very simple thing that just quite simply fades the screen, unsurprisingly. It looks like this. It is a singleton, as you can see. It has a pipeline, graphics pipeline object. It has a binding group, which is sort of like my own kind of abstraction on top of NVRHI, which brings it a little closer to my own GFX API RHI thing of the past. What else do we have? We have a VB, an IB, and a CB. Vertex index and constant buffer. That's about it. And pipeline layout. Right. So I think it actually it comes from this. Let's have a look here. Right, so binding layout item. We create these. We probably create a pipeline layout out of them at some point. Here we go. Here's the binding layout. Is that the pipeline layout, or was there a separate pipeline layout system? Pipeline layout. Layout. There's no pipeline layout thing here. I'm just like, I honestly don't remember anymore. Right, there's an input layout. That's probably not what you're talking about. You're probably talking about the binding layout, right? Correct me in the chat if I'm wrong here. But assuming we're talking about the binding layout business, you have to fill in one of these binding layout descriptions, right? And I think that quite simply just comes from my shader reflection. Yeah, then create a binding layout out of the binding layout description. So yeah, I think we create like a few of them. Go here into init again. We have a few of them, right? Binding layouts, and the binding layouts are then used to create the actual pipeline description, right? Or rather, we add them to the pipeline description that we can then create pipelines out of, if that makes sense. Let's look at where we're using this, for example. For example, we should use it in the screen fade, and here we go. So let's make this a bit larger for you guys. Vertex attribute desk binding set desk. Oh, right. The vertex attribute description is actually the input layout. That's related to that. We can look at that separately. Right, so we create an input layout like this. Here's the NVRHI pipeline description. It's probably created up here. Yes. You can see I actually have like 2 of them. I have a GFX API pipeline state description, and then I have an NVRHI version of that. These are essentially like the same thing. They're just like basic different RHIs, I guess. If you go have a look here, you can see that it has many of the same things that the NVRHI one has. And yeah, so we have them here. We fill in the GFX API one just by hand like this, and then we actually convert that to the NVRHI one. So we just go in here and we just assign basically every every value. Whoops, now I'm breaking my own code here. Just assigning each value to the equivalent for the NVRHI stuff. Resetting the shaders just by assigning them. Basically going through each and every field and making that match. Then we get an NVRHI description and we create that. The input layout can be gotten here from the vertex format. So this is related to your your vertex attributes, right? Vertex attribute description that you spoke about in the chat there. So I have my own vertex format class, which looks like this. It's basically just like a list of these attributes. Attribute is right here, also very simple. The benefit of doing it like this is that I can just deserialize this directly from like the shader file or whatever. So that's kind of neat. And then I bet this guy is converted. Yeah, you're looping over all the attributes in the vertex format, and then you're copying them over. Yeah, and here's some notes about the semantics that like NVRHI and GFX API do differently. But yeah, it's essentially just like you have this code, which is kind of like general purpose. You can use this for any vertex format, and it should work. And then you have this format, which is the converting the pipeline description. You know what is it? Description? I guess it is. Yeah, description. Pipeline description from the source one to the destination one, which is the NVRHI one. This is also just general purpose. It works with any description. And then you have the actual thing that you want to render, right? So this is the screen fade one. You need to set up the state for that. And that's fine. However, if you have a material, the material sets it directly, right? For the material, you actually go into the material editor. Let's bring that over, and you can just set here, right? This is essentially like your description. You can you can set the fill mode to be wireframe, cull mode to be the front or none, whatever. Depth bias. Many of these are just like directly set there in the description, and then you do the rest of the way the same way. So the materials are kind of like they have a default one which works for most cases, and then you can go in here and mess with that. So I think that should be basically how I do it. Alrighty then. Now, let's have a look what we're gonna do today. If you've been looking at my stuff from Discord lately, you probably know what this is all about. So I have this node-based system, which we can actually. Let's not do Timbre. Let's go directly into Merlin. So Merlin is one of the systems that use node graphs and bases, and Merlin is kind of like the most problematic of these things. So we have a node graph like this, which is kind of annoyingly sitting above the slightly darker lines here, specifying the origin. This is a particle effect. We can see the preview here. If we open a preview player for ourselves, we can play the effect, and we can see it's just like a test effect. It kind of spawns something, which is this diamond. So block out. No, that's the material, but this is the mesh, the diamond mesh. And we can put something else here. We can put a cog there, for example. And if we play it now, we spawn cogs instead. How beautiful. beautiful is that. And then we have a material, which is just set instance color, so it takes the color from the actual instance values that we write there. We emit some particles, we set their velocity, we update the particles, and as we are updating the particles, we set their color, and then the color is figured out from this sort of thing here, so we can just update that, and now we have a different color there, and it's all well and good. The problem with this is that this is kind of slow, because this stuff was never actually meant for particles in the first place. I made the system originally for doing audio processing, and for audio it's quite good enough. And it was later also used for the mission scripting, but for particles it's been kind of slow. It's actually been like so slow that if you have the game running, if we open the game again here, let's see, where is my command line arguments? Yeah, we can just go directly into the refinery. And let's maybe mute the thing immediately. Oh, loading is a bit slow. I don't know what that's about. So if we have a few vehicles here, let's do like test vehicles. We get a few vehicles that we can order around here by just asking them to come to us like this. We now have a few vehicles that have this well, actually none of them really do, because they're driving so slow. Now we can see some particles spawning. I made some measurements here that, like, if these 3 vehicles drive to you, kind of like on the other side of the map, sometimes you get something like 30 or 40 millisecond update times for all of the particles in the level, which is kind of crazy. It's like I wouldn't want them to be like a single millisecond for this basic particle, but and then yeah, we also have this somewhat complicated smoke pillar thing here. But regardless, it's way too slow. Specifically, the update is way too slow, and and it is too slow because those node graphs are interpreted, right? There's an interpreter which is in itself is not terribly slow, but the way that the data flows through these node graphs is just super slow. Let's go back here, because like we don't really know how the data is going to flow when we export this thing. Like, yes, we know that this pin is connected to this pin, and we know that you know, this expects a float and this actually outputs a float, things like that. But some of these like vectors are, for example, like vector variants. You can plug in like 2D vectors, 3D vectors. It just has to do like a whole bunch of like figuring out at runtime to be as flexible as possible. And so that doesn't really fly with particle systems. Hello Aswin Mdev B2V. Right, so it's kind of like just marshalling the data from node to node, which is slow, and then just like doing it, you know, many thousand times every frame, because we have just like a few particle effects that have like maybe a few tens of particles. That won't fly. I haven't really figured out how to solve this until I just kind of started trying to solve it, and I think I have a pretty good system brewing now, which we're going to work a little bit on today. Lizard Demon says, normally I just do shader particle effects. Yeah, we've been talking about doing GPU particles for for a long time on the Discord now. GPU particles would be better in some ways. Yes, they are more efficient. GPU particles are they are kind of like by necessity a very bespoke system, though. Like you kind of need to make it. You need to write the system in such a way that like it is efficient to do in like a compute shader or something like that. And the system that I have going here, which is called actually Sprinter. Sprinter is the sort of like execution engine for these guys. These execution node graphs, as I call them. It's very flexible, and it works almost like on a cooperative multi-threading or multitasking principle, meaning it works kind of like coroutines or fibers. And that doesn't really work with GPUs at all. Now, it could be argued that like this is not a very good base for a particle system, and why would I build it on top of this? Well, the reason for that is just that I have this thing, and it just comes with a whole bunch of different nodes already working. So we have like logic nodes, we have select by index, random branch, we have a for loop, we have a repeat node, we have a delay node, all kinds of things. And we have math, we have vector math, smooth step vectors, swizzle vectors, lerp vectors, decomposing dot products, functions. I have just all of this stuff, and it kind of just like works already. And so I was thinking like, okay, how do we make this Sprinter execution faster? Because if we make it faster and we make it nice enough to use in its faster form, it will benefit not just the particles, but just like everything else, all the other things that use these node graphs as well. So if we made a GPU particle simulation thingy, which wouldn't be a bad idea, but if we did that, the audio side would not benefit from that ever, and the mission scripting would not benefit from that ever, that sort of thing. And the way I've figured I'm gonna try to solve this is by converting these guys to native code. Kind of like how Unreal Engine used to have something called blueprint nativization. I believe it's actually removed from Unreal Engine 5 now, but it used to be a thing in Unreal Engine 4. You could actually take your blueprints, which are kind of like similar to the Sprinter node graphs actually, and generate native code out of them. I'm not exactly sure why. I think it was kind of flaky or something, so they removed it or deprecated it, whatever, for Unreal Engine 5. But what we're doing here is kind of similar actually. So here we have a test node graph, pretty simple. Start here. This doesn't have anything to do with particles, you might be able to see here. But we start here, we print the string starting, and then we start repeating an action. So every second, because this is period is in seconds here, we print the text action. And then we have another, which is like simultaneously, these two are kind of running simultaneously here. Or you might say these two, because we're splitting off here. So this is like already something that like, how would you do this on the GPU? I don't know exactly. Maybe you could like time slice it or something, but like, I don't know how to do that. At least off the top of my head. So we have a track condition going on here simultaneously as this repeat node is running. And the track condition, tracks, is the effect time, so basically like how long this graph has been running. Is it greater than or equal to 5? And when that condition turns true, it causes this repeat node here to stop. So then it just prints stopping and then prints the time. And this has been my test case for this whole system. And here we can see, this is now, I'm just running this straight out of Visual Studio. As you can see here, from the Basis Tools solution, because this thing has never been sort of like deployed, right? The native code that we generate from this or shall we say, the node graph, this node graph here, burp, in native code form is now this. So it's about 470 lines, and there's some verbose stuff here. There's some comments and things that we sprinkle in here. We can make it tighter if we want to. But this is the whole thing in native code form. Well, not the whole thing, but the thing that like represents these guys. And we can see it's actually like updated in real time. So if we, what should we make? Like float compare, for example. Where do we have the compare node? Compare. That's right here. So you can see like the get result is like value 1, and then value 2, and then we have larger than or equal to value 2. So if we disconnect that, now it's 1 and 5. And if we make that like 3.141592, I can see it's updating here. This is a bit weird though. Oh, I know what happened. This thing is supposed to stay on top. That's why I'm confused that it actually like goes behind. And I know what happened. What happened is that I ran the old one, the old version, which doesn't have that, which like erased my settings for it. Let's just reset the Windows settings here. And now we should have it in a nice dockable fashion. So I'm just reset my Windows. Let's do editor log, goes on the bottom. Properties can go there. Effect preview I typically keep up there. Now we can see now this is dockable. First of all, you can drag it there if you want to. But perhaps more importantly, actually that's not the one we want. We want the code gen test one. Oh, that's not the. No, I'm just breaking my own layout here. Here we go. So okay, now if we go to greater than or equal, let's find that compare thing again. Compare node, float compare is right here. So here we have the code. If we like change that to like equal, you can see that it just changes immediately. Not equal, greater than, less than. And so the code is updating in real time here as we are actually making these changes. And if we delete that, then we probably, oh, we get a crash. Look at that. Look at that. That's not good. Trying to get data from input data pin which isn't connected and doesn't have inline data. It should have inline data though. That's weird. Why does it not have inline data? Probably need to do that again because it crashed, so it didn't write those things to the settings, right? So let's shut this down once, and now we don't need to do it again because now it's stored. Saves it on shutdown. There we go. So yeah. Anyway, this is very, as you can see, this is very sort of hot off the press. Oh, I know what this is. Yeah, it's this thing here. I bet it actually crashes if I just remove this pin here. Yeah, look at that. Exception unhandled. Trying to get data from an input pin which isn't connected and doesn't have inline data. So this is actually a perfectly valid case to have the node graph in. The code generation should actually fail here. And I kind of wonder why it just doesn't tell me that it failed. Now that I think about it. Let's see. Because we are generating code. This is all the new stuff that I've been working on for the past 3-4 days maybe. Get generated code. Right, this thing actually needs to, yeah. This thing actually needs to sit inside of the try catch here, right? Let's put it in there. Because we have specifically we have the error handling here for the code generation errors. there we go. Oops. Yep, and now we got error running code gen, trying to get data from in between, which isn't connected and doesn't have inline data. It's not very good like error for the end user. And that's something that I'm gonna have to actually fix. But now you can see now we can redo and undo this thing, and it kind of works nicely. So that's cool. Let's see. Have you seen the Daslang game engine scripting language? It's like Lua, but it gets C++ level performance in most cases. Yes, I have seen Daslang. It's been around for a while. Not super sure about the like speed promises there though. Like Lua, or shall we say in particular Luau / Luajit is very, very performant. Even just like standard Lua is pretty performant. So I'd be surprised if Daslang like outdoes Lua, except in some, you know, semi-fabricated benchmark thingy, which I don't really trust ever. But yeah, I do know about Daslang. It's one of those languages that is probably okay for almost every kind of game. They have good perfect tests against Lua, right? Define good. I know I'm being super skeptical about any kind of performance test made by someone who actually makes the thing themselves, right? It's perfectly, you know, it's perfectly fine that you have those, and especially if they are, you know, tests that anyone can run and verify. But if I was to make a scripting language, and I made, you know, 20 performance tests, and, you know, half of them were in half of them my language was winning, and the other half my language wasn't winning, I would choose the 10 ones in which the language was winning to put on my GitHub page or whatever. So yeah, it's always better if it's a third party making those tests. Even then, they can be kind of tricky to, you know, actually have sort of like sensible real world, you know, to have it represent like a sensible real world game project or whatever. But sure, I'm sure this is not to like diss on Daslang at all. It can be a perfectly good language. Anyway, so this is the code for this admittedly very simple little node graph, and this node graph, as I mentioned, is not very interesting. We can run it here. We can preview the thing here, and we can see what it actually outputs. The output actually comes here in this game debug window here. So it says starting, which is this thing here, and it says action 5 times, which is this thing here, and then it says stopping time 5, which is this thing here. So not super interesting, but still it proves that this works. However, we are running in interpreted mode here, just the good old interpreted mode that has been around for a while. How can we actually run this natively? Because this thing doesn't run on itself, like on its own. You can't just like throw this into a Zig project and press build and get a DLL, and then you run this somehow. It needs a little bit of code around it to actually, you know, make it into something. And to test this out, because like I said, there's not a system that's like really kind of deployed yet, because there's some files here that actually aren't even submitted anywhere, just completely untracked files. Here we have this code gen test effect. So it's basically like all of this. This is the same stuff that we just looked at. I've just quite simply copy-pasted it in here. And it's part of something that I call Merlin native. If we build this guy, this should build now. Let's make sure it does. It does. Cool. We should be able to go into zig out and into probably binary. And here we can see Merlin native DLL. So here's the DLL that we actually produce out of this guy. And then in the actual game, or in the runtime for the Merlin. Merlin is the name of the particle engine here. So it's all of this node-based code that's related to specifically playing back particle effects. There should be a define here. Yes, there is. Load test native lib. So I'm just have this hard-coded path to this DLL file here. There's one of those things that I haven't quite figured out how I actually want to, build all of these different effects into a single DLL. I have a plan for it, but it hasn't really been implemented yet. So I just have a hard-coded path here for testing this out. That's what's sitting behind this if-def here. And we can see that it just loads the file if it exists. We create a library, we load the library, and then we bind some stuff so that the C++ side can talk to the Zig side. And then in the game code, and I told you earlier, we're going to jump between a few different Visual Studios here, both the actual Visual Studios and the code versions. I quite simply have a hack here, so that if we press the debug pause, which is the P key on the keyboard, the debug pause is commented out. Instead, I have this little piece of code here which loads the effect, which is again hard-coded to be code gen, and it creates the instance of that and auto starts it. So we essentially like play a particle system if we press the P key without actually placing it in the world or anything like that, right? Let's go to, I'm gonna make those launch parameters be something a bit more. There we go. Depot is probably good. Let's use that. Oh, that's debug. Let's not go with debug. Let's go to release instead. So we go into release, and again we can see this output window here. Now if I press P, you can see starting, action, 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 and stopping. And it ran, what is that, like a 1/10,000th of a second over. But still, this is now actually running that native code. There's no interpretation there anymore. It's just all Zig code being run through the same sort of API. So the Merlin manager, or the Merlin runtime system, can now handle actually running both interpreted and native effects. If we go into effect instance, then we go to update. Actually, we go to advanced time. Here we go. This is like the ultimate place. If we are native, then we're actually calling there's a function pointer which points to the Zig side. We call update effect node graph. If we're not native, so we are actually interpreted, we just call node graph because we have the thing here directly. And so this advanced time specifically, this is the thing that takes a long time. This then on the C++ side goes into node graph, and this starts updating the actual graph by updating the cursors. The cursors are kind of like the instruction pointers. And if we are on the native side, we instead go to here, update effect node graph, which does some black magic here with both compile time and runtime code to figure out what kind of effect is this. And here we can see is again part of the stuff that I haven't done yet. As you can see, more graphs here. So generated section begin and generated section end. And And this is where I'm sort of like, I'm thinking that this is how I actually want to have this thing working. So in this switch, you have just one node graph currently for all of this. But as we build more of these things into native form, this part of the code would be generated, all of that, and it would just like put the correct ones in here into this switch one. But currently we just have the one, so we go in here. Actually, we go in here, update, and we call update, and then finally we go through the node graph.zig. We actually get into the code gen test, and we call this update here. And this now actually updates all of the nodes. And this, again, this is the code that we copy pasted out of that window in the editor. So there's a few sort of like few hoops to jump through to actually get this to work currently. And I only have this single node graph currently running in native mode. But my plan for tonight is to keep working on this. I would almost... oh damn, I did it again. I ran the old version again, and now we're gonna have to do this window business. You know what? I'm gonna remove this so that I don't accidentally run. That's the old version, the version that doesn't have the new window. And when I run that and then I shut it down, it messes with the window settings because it just like doesn't have that new window there. So I shouldn't be running that. I should only be running this new version through Visual Studio. Anyway, my plan for tonight would be to keep working on this system to eventually get this this particle effect running, which actually does some particle business, right? This plays some of these particles. It's a very simple system, but still I think we don't have like almost a single one of these nodes actually generating anything here. We do have the two first nodes actually are the same as in that other node graph we have already working. So the onStart, which is this thing here, this helpfully like prints the type of the node here, so we can see that okay, this is the onStart node. And if we turn on the IDs by clicking this little key icon here, you can see a number before each of these nodes. That's the ID, and the ID is also used here in the actual node class. So that's node 0. That would be that guy. Node 1 is of repeat node, and you can see yeah, that's a repeat node. And if we go to like 13, that would be this one. That's a color vector node. You can see it's here. But almost all of these other nodes, they don't have really like any code. You can see that okay, they do declare the input pins and output pins. This get particle data node has just like an ungodly amount of pins here, like 10 of them, and it's this guy here that just like returns a whole bunch of stuff, gives you a whole bunch of stuff, information about the particle that you are simulating. So we do have the pins, and it has basically a pointer, but it doesn't have anything else, and that's just because I haven't implemented those. So we only have node 0, which is this start node, and we have node 1, which is this repeat node. And none of these other ones are actually implemented. So I was thinking we would quite simply just keep doing that and see how far we can get. I'd be happily surprised, positively surprised, if we actually get this thing working today. But you never know. We'll see. Alrighty then. A little bit of water, and then we can start doing this. So, because this thing is so rough, because it's so fresh, it is a little bit of an experience to generate code for these guys. So the way that this works is, you select one node. They're gonna go like, okay, I'm gonna implement the code generation for like this onStart node next. And then what you do is you go into the tools solution and you search for the onStart node. And it would be this Merlin node specifically. Now here is that's the one of the two nodes that I actually already have code generation working for. So you can see it has this generate native code. The name doesn't actually matter here, but this native code gen attribute is the important one. This is the thing that tells the system, hey, when we generate code for one of these nodes, we're gonna call this thing, and it's gonna essentially use this native code gen context here to actually add the code there. And so we can see we set an update function, and this is just like inline Zig code. Now because of these verbatim strings, as these are called, the ones that have this at sign in front of the string, these treat the string, well, as the name suggests, verbatim. So all the new lines and the white spaces and everything are treated as they are. There's no like escaping anything inside of a verbatim string. So the indentation here is a little bit wonky because like we want specifically, you know, two levels of indentation here to make this thing like nicely show as having 2 levels of indentation here. But you can see this is the same thing. The first thing we do is we actually we ignore the self parameter because we don't need it in this particular case, and Zig gets cranky if we don't do anything with it. So we have Sprinter assert. That's the next one. We assert that we actually did come from the signal, because this is the on node, right? There's no input pin here. This thing is actually kicked off when we send the input signal. So we have those 2 lines there. Then we have exit through pin, and this is one of these places where, like, if we put another print, like a print node here, for example, if we connect this, you can see that, oh, okay, now we have 2 lines there. Now we're going to number 15 as well. If I copy paste that, put a 16, it just keeps adding those things, because you can exit through multiple pins, and they will all sort of like simultaneously start executing. It's not simultaneous, of course. It does one at a time, but for all intents and purposes, it happens at the same time. So that's pretty cool. But to have this thing actually be able to generate code like this on the fly, we actually have to have these things that I call fragments. So FGMT. At this point, we insert a fragment with the out pin which we get here. And then after that, when that is done, we continue the function, and we add this like return continue and the end of the function here. But yeah, this is not super nice to look at this code here. Luckily, you only kind of really have to do these once, and you don't really have to mess around with this anymore. But I'd like to maybe come up with a way to at least have this indentation be a little nicer here. We'll see what can be done. But like, this literally didn't work yesterday. It's been like my project for the weekend to get this thing to actually do anything. And so I'm kind of happy with the fact that you can just, you can just do this, and you can add a new one and then connect it here, and it just like appears there. It's just majestic. So, the third node here, or the next one in the order of execution, would be the emit particle. This is kind of a scary one to do, because this is the first. Does that always move down when I click it? Or is it just me? Yeah, it always moves down when I click it. Okay, I don't know what that's about. Yeah, this is kind of scary in the sense that I haven't really done any sort of particle work on the native side yet. So it's going to be interesting to see what this actually ends up doing. We can look at the interpreted side for that. So the interpreter also has some native code, and this is the code for the emit particle node. There's the code that runs at runtime if you run the interpreter. So it's not like everything is some sort of bytecode or anything like that. the interpreter quite simply just like puts pieces of code together at runtime and then calls that code. And so this is the update node function for the emit node. And we can see that it enters through this execution pin, and then it exits through this strange looking purple execution pin. The purple is the same color as this particle category. You can see all the particle nodes here are purple. And this means that this purple execution pin, now we're executing within the context of a particle, right? So the idea here is that like you can't just start the particle effect and connect one of these regular ones to that one. Like it doesn't even connect. Because like what is this? Set particle velocity. We don't even know what particle we're talking about here. So you have two sort of different modes essentially of running. You have just like the normal execution here, and then you have the particle within the context of the particle. And whenever you're in the context of a particle, the system automatically knows which particle you're talking about. So you can just do set particle velocity, update particle, and update color. And this update particle node is special in the sense that like this thing, as long as the particle is alive, this thing just fires. This update pin fires every time on every update. And then you can do whatever. Here we just set the particle color, but you could set, you know, the scale or the velocity or whatever on the thing. This fires every time we want to update the particle. Then when the particle dies, this fires once, and here we're again back to normal execution. So here you could, for example, just spawn a new particle if you want to. You could connect another one of these. That one actually. Connect another one of these emit particles here, and then just do some sort of unholy loop of spawning. You could connect that there. Actually, I think it should probably connect it to the update. Actually, yeah, that's the update one. Oh, we can't do that actually, huh? It's probably because of the loop detection not being turned off. It should probably actually be turned off. But anyway, that's not really something you want to do, but you should be able to do it. I think it's a bug that you can't do it currently. Anyway, so the emit particle node, currently in the update node, we assert that we're entering from the in pin. Well, there's no other pin to enter from. You can't enter from these data pins. But still, we check if we can emit particles. Like you can, for example, you can have a particle effect that you at some point you call release. Stop and release. Stop and release basically stops emitting particles, and then when all particles have died, then you release the whole thing. So that sets can emit particles to false. If that is the case, then there's nothing for us to do here. We need to stop executing this node. Then we go a bit further, and we use something called a particle store. We allocate a new particle from that, and that basically gives us an index. We're going to hold on to that index. But first, we're going to use that index to get to the actual particle pointer. This particle has some position, rotation, scale, color. Also has like lifetime, current age, flags. A lot of the same things that you can actually see, you know, here. You have absolute age, position, scale, velocity, that sort of thing. Right? So you get that particle, and then you read the input pins. So they're like these two guys here, the lifetime, and you get the renderer. So lifetime is stored there in the particle. We get the renderer ID, we store that in the particle as well. And then we look at the emitter shape. So if it's an emitter point, we just set the position to the actual world matrix. This would be the world matrix of the emitter. If it's a sphere, it's like around the emitter, and if it's a box, well, it's a box shape around the emitter. And then we do some bookkeeping here. Cursor to particle map is just, this is essentially like the way when I mentioned that these guys basically know what particle we're talking about when we are, you know, setting the particle color, for example, or setting the particle velocity. They need to somehow know which particle we're talking about. Well, it comes through the cursor to particle map. So we need to insert for the cursor that we currently are executing, we're inserting the particle index and matching these guys together. And then we're also, and this is the important part here, we're also setting the current particle index. This is the one that the other nodes will then read as we go forward through these purple pins. This is how it knows the current particle index. And then, as I said, this update node here, it fires this update pin multiple times. So it essentially like loses its context in between frames, essentially. And to be able to resolve this current particle index again for the next frame, well, it goes through this cursor particle map. That's why we have these two things here, the cursor to particle map and the current particle index. And then again, we can do the same thing. So we look at the set particle color node, for example. Particle color node, well, this guy actually uses the current particle index to get a pointer to the particle. And then you can just set the color of the particle. It's that simple. So some of these are like really simple. Simple, small little nodes. And some of them are really tricky. So I'm thinking like the emit particle is kind of tricky. The update particle is also kind of tricky, I bet. Probably not quite as tricky as the emit particle node. So the update node also handles like killing the particles. Let's see here. Make sure we have a particle map to the current cursor. That's the cursor particle map. Then the update of this particle currently goes like this. Update the transform based on velocities. Fire the update out pin to let the user affect the particle's data. So that's like exiting here. And then you can plug in other nodes. And then particles, update the particle's age and check if it has died. So if it has died, which we check here, we remove it from the update or the cursor to particle map. And we free the particle so that some other particle can take that space. And we exit via death. That would be this pin. Bloops. That's it. That's basically how it works. So we should look at converting these guys into Zig, the native code. And not just that, we should look at writing that so that we can actually generate that code. So it's going to be a little funky, maybe. We have a particle mesh renderer. That thing actually, let's see, mesh renderer, no, mesh particle, yeah, mesh particle renderer node. Here we go. This thing actually gets a renderer for the settings that we have given it. So we give it a mesh, we give it a material. And these are checkboxes. So whether or not to sort the particles and whether or not we have light probe support. And then based on those values, we get a renderer. This is a little hairy maybe to do on the Zig side. So we're probably going to have to actually like expose this functionality from C++. The important part here is that we store this renderer ID, which is really just a number, uint32. And that number is the thing that flows through this output pin here. So renderer, we can see in the emit particle node that we set it to be the invalid renderer ID. But then we get the input data pin for the renderer pin. That would be this pin here. And we store it here in this one. So these are like references. There's an ampersand there. So this thing actually like writes it into the particle there. So this thing sets up the renderer, registers it with all of this data that we specify here. So the meshes, for example, but then it outputs this ID and we store that ID in the particle. So the particle knows which renderer is actually being used with. Right, okay. I think the rest of these should be pretty simple. Get particle data, of course, has just like a lot of a lot of nodes. But the code is not actually very tricky. It's just like, okay, we get a pin value, and then we have a switch case for, okay, which value do we actually want? Now this is the interpreted one, so we don't need to do it with the switch in the code generated version, because we can just hard code it to be, if we're reading the scale and we plug it into some place, we can actually already in the code generation phase go like, okay, give me the scale. We don't need to check like, okay, which thing are we gonna read here, because we can immediately see that, okay, we're reading the scale. So that's one way that like this native code version is going to be significantly faster. We have some color vectors. We have a lerp vector node. We have a remap float node. These are not actually like particle specific at all. These are just like, you know, general purpose math nodes essentially. Same thing with this random 3D vector business here. Anyway, I think I'm quite simply just gonna start porting one of these nodes. Don't know exactly which one to do. Maybe we'll just start with the emit particle node, because it's probably not a bad idea to go with that. And I'm thinking I might actually want to just like handwrite this code first. So handwrite it like this, so that I know that like, okay, where do we have node number 2 is here, emit particle node. And then when I have it handwritten, we can actually even try to compile it. Because look at this. If we take this code, essentially everything except I think those two, because we're gonna have to actually give some values to those two. I'm gonna take everything under that and just copy it out of here. I'm gonna close that down. Actually, let's do it one more time. Let's do it with that's the wrong project. Let's do it with a node graph that I haven't messed with. I messed with that so much when I explained it to you guys. That let's do color test, and now we're gonna do the same thing. So copy all of that, copy, shut that down, and now we're gonna paste it into here. So here we can see, oh, game Merlin effect testing color test. Yeah, I already put the path there. So this is just waiting for me to plonk in this new piece of code, and this is how I have developed the first one as well. So when you get something sort of working, or at least in a state where it should compile, you can bring it into here and then make sure it still compiles, right? So now we can actually like handwrite the code for what this emit particle node should look like in here. And when we have it working here and it actually compiles and everything, at that point we can bring it into the code generated form. Work kind of backwards from that. Now if we build this thing, it should definitely build, because I don't think anything is actually even referring to this. So we're gonna have to actually bring it into here. And this is code that's gonna be generated. Graph. Difficulty writing graph here. So import, and this would be game, that's the color test, right? So in this node graph store.zig, there are two sections that I think are going to be generated. They're pretty basic to generate. You can see here's just a list of all of the nodes that we bring in, and I just give them a numbering like this. Doesn't exactly matter what their names are, as long as they're unique. And then we have another one, which is right here, and it's essentially just like the same thing. We need to list these out, but we need to implement all of these methods for all of the nodes. So here we're gonna have node graph 1, resource path hash is true. So this is a hash node graph. if it's that one or it's that one, then it's true, otherwise it's false, right? And when we create the node graph, again, we're gonna have to do it like this. So if we get the node, the resource path hash, we have to create the node for that particular, of that particular type. Effect pointer, first bucket pointer, like so. Should be exactly the same, just that this is 1 and that is 1. And you might be wondering, okay, why do we need to do it like this? And is there a better way? And there might be a better way, but this is actually a pretty good way. Because first of all, this is super simple to generate. If you have just a piece of C# code or something that generates this stuff. Essentially, like these guys are just gonna sit in a loop and you're gonna increment these numbers here. But the reason we need to actually have this sort of like adapter in between is that the C++ code, of course, doesn't know what kind of node graphs are sitting in that DLL. It just knows that, okay, we are requesting the node graph with a certain path. So basically this thing here, game/Merlin effects testing color bin Merl effect. That is the path that the game code can be sending. Alternatively, it can send the hash, which is a string hash of this thing, which we have here, right underneath it. And so then the DLL needs to like go, right, I need to somehow map that type onto one of these graphs that I have. And this is the way we do it. So have a switch with the effect type, which is a U32, that's a string hash. And then we match it against those. Graph number 0 or graph number 1. So now if you make some like super obvious like error here, let's put like an F there. So the const is no longer const. And now if we build this, now we should get a, yeah, that's not good. So let's take that back. And let's see, does it build now? And it builds, cool. So now it's pretty clear that this code here is actually being used. And we can turn our attention now to the emit particle node. So let's again take it here. I think I'm gonna probably put it on my other screen so I can reference it while I'm working. And right, so we have a few things. First of all, we have an update node function here. We also have an update node in the native side, which is going to do essentially everything. We never stay in this node for very long, right? We just go through it, we emit a particle, and then we exit the other side. Some of the nodes we actually stay in for quite some time, like a delay node, for example. We can stay in there for like forever, basically. At least in theory. But here we basically just call this once, update node. We only really have one entry pin that we can use, so we just assert that it is the in pin, and at the end we exit out of this. And then we need to return this sprinter requires us to return continue or stop, so we just return continue, no biggie. And so really, our job here is to take one of these update functions here. There's the emit particle node, and the update would go here after the init function. I can comment that stuff out. So okay, we have an input pin. That's the execution pin. We can do the same kind of assert here. So let's do assert. We need to give it a source location. We assert that the entry pin index is int from enum input pin in. There we go. So it's that one. These other ones are data pins, so we can't actually enter from them. So that's sort of like the first thing. The next thing to check is if we are actually allowed to spawn a particle. So let's do self.create kernel dot can emit particles. And if we are not allowed to emit particles, then we need to return stop. Right. That would be that. The next thing we need to do is we need to allocate a particle. So if we look here at the C++ code, this thing goes through UD, stands for user data. This is how you can access just like particles and just general stuff on the C++ side. But yeah, we go through the user data, we get a particle store. And the particle store has an allocate particle function, has some other stuff as well. Allocate particle, free particle, and we get the index. We're always running with the index here. Particle index, and then we free using the particle index. If you actually want to get a hold of the particle itself, then you use this get particle with the particle index. That sort of stuff. We don't really use this with the native one. I've created a new system for this. And you can see here, SOA, so struct of arrays, particle bucket. So the idea here is that we get one of these buckets from C++, and C++ allocates these buckets, or allocates particles always in a bucket. And a bucket has 256 particles in it, right? So you no longer allocate a single particle. Instead, you allocate a whole bucket, and you can see that all of these fields here are arrays. All except this bookkeeping data here at the end, which counts how many active particles we have in the bucket. But basically that's the idea. So you get a bucket from the C++ side, and you essentially reserve yourself a particle from that, right? So we need to do this ourselves now here in this emit particle node. I'm wondering though if we should actually generate a little bit more code than just the particle emission code, and actually create like a helper function for this, so that the node doesn't actually have to do all of that on its own. That might be kind of useful. You can see here in the way this code is generated is that we have a bunch of nodes, node 0, node 1, and so on, all the way to node 14. And then at the end we have something called a kernel. The kernel is essentially like the thing that has an instance of all of those nodes. So here we can see that it has all of the nodes as its members. It also has a bunch of other like Merlin things. So here's essentially like the user data now lives in the kernel rather than in a user data struct. And this code is also generated, and we can actually probably create new functions inside of this guy if we wanted to. So we could have an emit particle function here if we wanted to in this kernel. And I'm wondering if that would be a good idea. So basically what that would give us is, let's do pub fn allocate particle. We give it a self pointer. And yeah, I don't think we need anything else. Just need the self pointer because it's a member function. And then we give it return rather Merlin native particle index. So we're still working with the indices. Well, the index isn't really enough. Like a single number isn't really enough. We can index into this bucket and go like, okay, we have the particle at index 0 in the bucket, right? But then you can have multiple buckets. So how do we uniquely identify a particle using just a single value? And the way I've done that on the C++ side is by splitting it into two, essentially. So if you have a particle index, this is also a uint32. And we have a function here for combining the indices. So we have a bucket index, and then we have a particle in bucket index, which gives us the the full 32-bit index. So two 16-bit numbers, essentially. And we can do the opposite one, which we take, you know, a particle index, and then we split it into one 16-bit value, which is the bucket index, and one which is the bucket or particle in bucket index. So we're gonna have to do something similar than the zig side if we want to actually represent it with just a single value. But yeah, as far as the node is concerned, we're essentially just using a single value to identify the particle. And so when we ask this, hey, allocate the particle, it's pretty handy if it just returns a single particle index here. Similarly, we're going to want to have a free particle function. So self and particle index, right? Like that. Oh, we need the void at the end, of course. So we can give back the particle to the system essentially, and then this kernel would be the one that actually figures out, okay, do we have any particles, right? Do we have any buckets that have free slots? And if we don't, then we allocate a new bucket, and in the end we give the particle to the thing, quite simply. So you can see I have a little bit of sort of scaffolding in place here already. When we create one of these effects currently, we get a bucket assigned to ourselves. Let's go have a look at the node graph store. You can see create node graph. It gets, among other things, it gets a pointer to the first bucket pointer. And the first bucket pointer is actually placed in the particle bucket's number 0 slot there. And then we set the particle bucket count to 1. And so that's handy, because that means that this particle buckets array here, which has a maximum of 32, it's a maximum bucket count that we're going to support. This guy actually already has a bucket in it, and this is set to 1, right? So the first thing that we can do here, and when we allocate a particle, is we can figure out do we have a bucket that has free particles, and if we find one such bucket, which of the particles in the bucket is free. And I think we do that with just a straight up linear search on the C++ side. We're going to do the same thing here as well. Right, so we iterate over the buckets, get the bucket. If the active particle count is less than the maximum number of them, so basically if there is free space in here, then we go and figure out which one of those guys was free, and we mark it as not being free, and then we do the combine indices thing that we just looked at. So let's do that. Let's do the same thing here. So I'm gonna do 0 to self bucket particle bucket count. That gives us I. Maybe it should give us I is fine. I is fine, at least for now. So that's the. Maybe we can be a bit more specific. Let's call it bucket index, like so. So, if self particle buckets bucket index active particle count is less than I think it's Merlin native max particles per bucket. Right, so at this point we can go like, there should be a free particle in this bucket. If we don't actually come here, if we run through this entire for loop and we haven't found a single free particle yet, that means that we don't have any buckets with free particles. So that means that we're going to have to actually allocate one. And we can do that with, let's see if we can find this. Bindings, FB, Merlin effect. That's not correct. Yeah, it just hasn't updated. Let's restart ZLS here so quickly. Make sure it actually catches my new... Yeah, get effect time was removed. It was actually never used. But here we can go. Allocate particle bucket. And the thing it actually wants us to pass here, if I remember correctly, is self.Merlin effect pointer. So the C++ side knows, oh, where are we going to actually allocate a new particle bucket? Particle bucket gives us... what does it give us? It gives us... a U64, but I don't think it should be a U64. I think it should actually just be... a pointer to one of those guys. So let's actually change that. Let's see here if I can just do it like this. I'm not sure. Here, reveal. So it's called SOA particle bucket. SOA particle bucket pointer, like that. So now, all right, this is a little bit annoying. This assumes that it sits in basis bindings, which of course it doesn't. It sits in Merlin native.soa particle bucket, so I have to change that by hand. But other than that, it looks pretty good. So this should now actually give us one of those guys. So let's do. Let's see. We can do self particle buckets, self particle bucket indices, isn't it? Particle bucket count. Yeah, there we go. Particle bucket count. And then we need to actually bump that because we have one more. So now we have the latest particle bucket count has, well, it should be completely free. So we can, at this point, we can just go like allocate new bucket and mark the first particle as active. So basically what we can do is just blindly select the first particle. Particle bucket count, or particle buckets rather. Yeah, okay, this is a bit confusing. Let's do it like this. Let's do const new bucket index. That would be this, right? If we have one and we allocate the second, then the index of the new one will be 1. Yep, that looks good. So now we can just use that. The new bucket index. And we can set the flags for, quite simply, number 0 to be, in use. But we don't have a value for that yet, so we're gonna have to figure that out as well. But anyway, let's comment that out for now. And we can see what the next step is. So here on the C++ side, we've done essentially the same thing. We've allocated a new bucket, and we get the new bucket like this with the back, because these are just sitting in a vector. We set active particle count to 1. We reset the first particle, and then we set its flags to active. This is the thing that I just spoke about, right? New bucket index. We do essentially the same thing we did there, and then we do the combine indices business. Okay. So let's try to do all of that. So active particle count, this should be set to 1. We should have a function here to reset a particle. Basically do this reset call here. So reset just like sets all of these fields for the particle to some sensible values. So let's create one such function here in Zig. I think I'm gonna put it here after this SOA particle bucket type. I'm gonna take the C++ version here and just comment that out so we know what we're dealing with. I'm gonna do pub function reset particle, and we need to give it the bucket like that, and we need to give it the index in bucket, and that can be like a, I don't know, usize, whatever, void. And so then we have bucket. Oh, that's not how you do it. That's how you do it. Bucket. There we go. That's a pointer. It's confusing when you do, like, you know, half of the time you do C++ and half of the time you do Zig, or perhaps even worse yet, you just flip between them all the time. It can be kind of confusing sometimes when you're like, oh, okay, it needs to be the other way around, right? Index in bucket. I think we're just gonna call that I. I know what I mean. We don't need to be that specific. Okay. So that would be that. Total lifetime. Bucket. Total lifetime I. 0, 0. Then we have bucket. Current age. Renderer ID. Well, renderer ID. I wonder if we have invalid particle index. We don't have an invalid renderer ID. What is that? What's the value of that? Then it probably needs to match the C++ side. Let's have a look-see. Let's have a look-see. Right. It is that. So let's go to Zig. And we do, this needs to go in Merlin native. So first of all, we have a particle renderer ID, which is also U32. So we have it just like a bunch of these. Oh, there we have it actually, particle renderer ID. There you are, my friend. Let's do pub const invalid particle renderer ID, and that would be 0xFFFFFFF. 8 Fs. Like so. Yep. That's good. We can take that away. Yeah, you can see here that we need to keep some of these things just in sync with the C++ side. There's the opposite comment there on the C++ side for keeping them in sync with Zig. Right. Renderer ID. That was that. So we can take those guys away. Then we have position. Position I. And what is this actually? This is a vec3. This is a vec3. Cool. This is perhaps slightly confusing because I do have a vector3 type in Zig, but I actually don't have it here in Merlin, because I try to actually use as little as possible of the code that I normally do to keep the compilation of these particles to a minimum. So I have just a very few select things brought over from the main sort of Zig code base. And here I'm wondering, why does this thing actually not? Oh, it needs to be inside of this one, doesn't it? Set XYZ. Yeah. yeah, I think I actually kind of decided I'm not gonna have member functions for those guys this time around. So instead what we're gonna do is we're gonna do sprinter vec3 set xyz, and then we have address of bucket position I, and then we have 0 0 0 like that. That's how we're gonna reset that. Rotation as well, and scale. I may end up reintroducing some of that sort of quality of life stuff that I have in the main Zig codebase for the game. But for the time being, we're gonna go like this. So linear velocity, that is probably, oh, that's actually also a vec3, is it? Yes, it is. Of course it is. Of course it is. So linear velocity, and color is a vector 4, which apparently I've set to white, and I reset these guys, which I guess makes sense. Like so. And then the tetrahedron index, that is that's something that's related to the light probes. We don't really need to worry about it here. The C++ side kind of takes care of that for us. Right, it's just 0 like that. Oop. There we go. Yeah, we don't really need to care about that right now. We kind of just need to carry that value around with us. And then we have the value storage, which I've done like a mem set on. This is quite simply just a type that has 16 floats that the node graphs can store data in. How do we want to set that? We want to use memset here. Maybe we do. Maybe we do. So that would be bucket value storage. No, value storage I and data. And I think we need to do something like that, right? Oops. And then element would be 0. I think that should work. Do shout in the chat if I do something wrong with these things. It's entirely possible. I haven't done like a whole lot of mem sets in Zig, but I think that's how it wants us to do it. Like, I believe the mem sets in Zig are a bit more intelligent than they are in C, where like you're essentially always working on bytes. So this should work in the sense like we have this data here, which is actually an array of float 32s, so 4-byte elements. I think we should be able to just do it like this, where we're telling it to set each element, which is 4 bytes, not 1 byte, to the value 0. And that should work, but I'm not sure. I guess we'll find out eventually. Anyway, now we have the reset particle business done, so we can go back to our node here. Or actually, it's not the node, it's the allocate particle business we are still in. So at this point, we can go self dot. Let's think about this a little bit. Probably want to go after that one. Yeah, so self, or rather Merlin native SOA particle bucket reset particle, and we give it a pointer to the bucket, which would be self.particle buckets new bucket index, because it's already a pointer, and we reset the first one, which is index 0, right? Something like that. And then we need to do this. We need to do this this flag business here on the C++ side. So we have this flags value, which on the C++ is a uint32, and it's essentially like these bitwise flags. So it can be none, it can be is active, or it can be waiting to be killed. This can be set by any node that wants to kill the particle. The particle update node reads it and does the actual work. Yeah, makes sense. Cool, let's look at how I've done some of those bitwise thingies in Zig. Let's look at it here. So I have actually quite a few of these. We just have an enum. Can be a type U32, that's fine. Yeah, we can copy that one. And we'll bring it into here. So that would be particle flags. And then we have these three types here. Bloops, like so. And this asInt is just a handy way to actually... It's nice in Zig that like enums can have member functions or methods, whatever, and you can just call .asInt, and then you get it as the U32 there. Don't have to write this longer int from enum. Right, so what we're gonna do here then is replicate what we have in the C++, on the C++ side. And that would be self.particleBuckets, new bucket index, flags, and 0. We're working with the first one here now, always. This would be Merlin native, SOA particle bucket, particle flags, is active, asInt. So we mark it as being in use. That's cool. And then we still need to do the combine indices and return. So again, we wanna return a single U32-bit number, which uniquely identifies this index or this particle, and we want to combine essentially this index here, the new bucket index, and the particle index, which here is just 0. So we can do actually new particle index is 0. That's probably a comp time int, yes. It's comp time integer. I'm going to combine these two as 16-bit values into like one 32-bit value. And then we want to do the split on the other side. And I think I had some handy code ready for that. Let's see. What does my note say? It says timeline component base. I had some timeline component base. This is from the game code, but it's still Zig. Right, so this has back event network data. Write the event index as a U16 in the first bytes, and the rest of the U32 can be used to flags and other stuff. So yeah, we have two 16 bytes essentially. We just write this weird, like, unsigned one byte thing. But still, what we get out of it is a U32, and then we unpack it, and we do this. We do the other way around. So we give it a U32, and we get out essentially like two 16-bit integers. We just treat them as just a U32 and a boolean straight up. But we can use this read packed uint or read packed int and write packed int stuff here to do the same thing. So again, let's go back to SOA particle bucket, and we can do We can do pub fn. Let's look at how the C++ side did it. It's going to be here. So these are the C++ functions for doing this exact same thing. So we have combine indices, get out a particle index, and then split indices and get out two 16-bit values. Awesome. Okay, good. So let's write this in Zig. Let's do pub fn combine indices, and we have bucket index use 16, and we have particle in bucket index. I'm just being super clear here what this actually is. Oh, boo, what pub. And this would return a Merlin native particle index, which is a 32-bit value. Right, so that would be basically like this thing. Back event network data. Would it not? Yes, I think it would. So we create a memory piece of memory here, which is U32. Then we write the first piece of information, which is the bucket index, and then we write the other one. I'm gonna actually just get it like this. This is also going to be a uint 16. The byte of or bit offset is also 16, and then it's that thing. I'm going to do int cast there as well. That should be good. And now we can just return memory. Right. So we have a piece of memory. We can actually even use this alias there. We have a piece of memory, we initialize the 0, then we treat it as bytes, and we write a packed int of type U16, and we don't actually even need to cast this, but maybe we should, I don't know. Let's see. Yeah, we don't need to cast that. It's fine as it is. Into the first 16 bytes, 16 bits, we write the bucket index. Into the rest, we write the particle in bucket index. Yes, good. And then we do the opposite, and the opposite is pub fn split indices, and we give it the combined, which is the particle index, and we get out the bucket index and the particle in bucket index, and we get them as pointers. Right? Like that. So I'm sure there's going to be a little bit of casting there, because here we're using specifically 16-bit indices. So that would be bytes again, and then bucket index is that. I'm going to take that away. Bucket index is that, and then we have the other one, which is that. Skipped to end, whatever. Yeah, it's the same thing, we just have a different offset, so I'm going to copy that instead. Just put it there, copy particle in bucket index there, and give that the correct offset. And that should be it. And we're sort of undoing the index split. Yep. That's good. That looks good. So now, like we're going on so many tangents here. I'm sorry about that. We're going on so many tangents to actually be able to create this emit particle node here, but that it is what it is. Can't be helped. So combine indices and return. Right. So now we can just do that. We can do Merlin native SOA particle bucket combine indices, and here we need to do now int cast to cast it into a 16-bit unsigned integer, and we have the new bucket index is the first one. Second one also requires an int cast, and it's the new particle index. There we go. And now let's compare this against the C++ version, so we haven't like forgotten anything. So if we don't have any free particles, and yeah, I'm getting to this part soon, but let's do the no free particles path first. So we allocate the new bucket. We do that here. Then we get the one at the back, which we essentially do here already. New bucket index. We set the active particle count to 1 here. Particle bucket count is 1. Yeah, okay, we need to do that as well here. That's good. So we set the active particle count to 1. That's that one. Then we reset the thing. That's the next one. Then we set the flags. So self particle buckets, new bucket index, new particle index, and that's the flag. Then we have already gotten the new bucket index, and then we do combine indices, and that is exactly that. So then we have this stuff in the for loop that we also need to do. So there should be a free particle in this bucket. We've essentially come like here. What's that? Right, we're keeping the, okay. Yeah, that's the bucket index. That we already have here. So that's fine. We don't need to store that. Then we need to iterate over all the particles in the bucket. So let's do another for loop here. For 0 to this would be Merlin native max particles per bucket. And what do we call that? We call it P in C++. So let's call it P here as well. And then we need to check this flag here. I think they should be basically the same. So we have actually, let's get a pointer to the bucket going here. So we have a bucket. This will be self particle buckets bucket index. I guess we can already do it here at this point. So if bucket flags P and Merlin native SOA particle bucket particle flags is active equals 0, and we probably have to do the double parentheses there as well. So if it is not active, essentially, then we make it active. We reset it, we make it active, and we bump the active particle count like that thing there. So resetting would be this. Yep, that's the bucket. New particle index would be P. That's the resetting, and then we have the setting of the flag. So that would be basically this thing, except we can just use bucket and P, and then we need to do bucket active particle count plus equals 1, and then we can do the combining of the indices. So new bucket index, that's just bucket index. We haven't created any new ones, and the particle in bucket index is P. All right, phew, that was quite a lot actually. Yeah, let's take the comment there and put that here. And remember that we are actually working here in generated code. This file is just entirely generated, or it's going to be entirely generated. So we're going to actually have to add this to this kernel thing here, so that this guy, when generated, actually just outputs this. Of course, it's kind of easy because this thing is going to be the same every time, so we can essentially just copy paste this into the generation, and it will just output it as is. It's not super tricky in that sense. Then we also have the free particle, which I already created the stub for here. So here we need to split the indices. We have the particle index coming in. We want the bucket index. We want the particle in bucket index, and then we want to split it. Actually, I can just probably take all of this and again put it in comments here so that we can see what we're doing. So let's do bucket. Bucket index. It's going to be U16, and particle in bucket index is also a U16. And then we do Merlin native, so a particle bucket and split indices. And we do particle index, address of bucket index, address of particle in bucket index. So now we have that part done. And there's some asserts. Some of these we probably don't. Well, we can maybe put them in. Doesn't hurt. I'm just going to do asserts without any message. This would be bucket index is less than Merlin native. No, actually, this would be less than self dot bucket count. And then sprinter assert particle in bucket index is less than. This is Merlin native max particle per bucket. I've changed the names slightly to these two for these to make more sense essentially. Righty-o. So what we need to do here is we don't need to get any particles because we don't have a particle class anymore. We might want to assert that we are active, and then we want to set it as not being active, and then we want to decrease the active particle count. That looks good. So let's just do basis assert, or not basis assert, sprinter assert. Might take some of these away when we actually know that this is working. No point in spending some CPU cycles on this after we know that they're actually working, but we'll see. So we're gonna want to make sure that the self particle buckets, bucket index, flags, bucket particle in bucket index, and early native particle flags is active. Isn't zero, basically. These particle flags are kind of annoying. It would be kind of neat to have them to shorten that a little bit. Particle flags like that. Let's use that instead, and let's do the same thing up here because this is really just very, very long. Not very nice. We need it there, of course. Something like that, right? And then so that basically covers that, which we don't need to do, and that which we just did. Yep. And then we need to remove it. I wonder, is it the same thing? Is it the same syntax here in Zig for actually removing a bitwise flag. I think it is, but let's see if we can find it here in the means namespace. Yeah, clearly is. It clearly is. So basically we can just take... Oh, that needs to be as int, by the way, like so. So we can take that one. That would be the flags. Bloops. And then that is the active part. We don't need any C-style castings there, of course. So self, particle buckets, bucket index, active particle count minus equals 1. Okay. Phew, all right. I think that finally now actually does this thing of freeing and allocating particles. Unless I made some mistakes here. But there's actually quite a bit of code here, so it's pretty nice to have these in like separate functions rather than having all of this stuff directly in the node. Another thing that we could maybe do is, if we don't want to actually generate all of this code and put it here, we could put this stuff into another helper struct and then actually just create a member of that here. That could maybe make sense. Yeah, that could maybe make sense. And then we would sort of like template it on the kernel. I say templated, it's not really templating, it's just, you know, this kind of thing where you have a type and you have a comp time type parameter here. And then you can use that as a member. We could do the same thing with this new helper type, so that it could refer back to this kernel type, because the kernel is the one that actually has the particle index, blah blah blah, all of that. Although maybe it doesn't have to have that. I mean, it's basically like these two guys that we are messing with, right? So we could actually call this sort of like mirror what we have there on the C++ side. We could create a new type that we call particle store.zig. Particle store.zig would have probably, first of all, these same declarations up here on the top, but then we would have a particle store, which doesn't need to have any sort of anything. No, like, no templated type parameters or anything, just that. And then it has these two functions. Blip, take those, particle store, and put them there. Right? And then it, of course, it needs to have these guys. So it needs to have those two. Particle store is right there. Yeah, I kind of like this. I think we're gonna go with this actually, and then we're gonna just add a member of this to the kernel, because the kernel doesn't need to actually refer to this at all. It just has one of these guys, and this guy doesn't need to refer to the kernel at all. This is much nicer. Let's do it that way. Let's not overcomplicate things. Cool. that should be fine. Okay, so before we go any further, let's actually make it so that when we generate the code, the kernel has one of these guys, a particle store. And it should look something like this, where we, basically like we take away these two functions that we just painstakingly created here, because they now live in the particle store, and rather than having particle buckets, it would have a particle store. Oh, we should probably go here first of all and actually add that type. So pubconst particle store import particle store, right? And then we do, in this case I'm gonna particle store. This would be like so. Maybe we can actually just, we don't need to take the module there separately. We're only interested in the particle store from that file. Yeah, there doesn't really be anything else in here, I think. We'll see. So now we have Merlin native.particle store is the type that we want. So that would be particle store with a small p, and it's of type Merlin native.particle store, and it can be just default initialized like that. Let's make sure that builds, and it doesn't. What? No field name particle buckets. That makes perfect sense, because now we need to actually assume that this guy has a particle store, right? And the particle bucket count in the particle store is 1. Still we have something funky. Let's clear the screen and build that again. Yeah, it doesn't build because this guy doesn't have the particle store. But again, we're gonna generate this code, so we just need to add it to the generation, and they will automatically have them. There we go. Now it builds again. Okay. Okay. Safe to say, this turned into a pretty convoluted, involved process. Not sure I would actually have I've started streaming this if I knew this was this complicated, but here we are. So I'm gonna keep doing it. Do let me know if you have any questions, though. I kind of go kind of quickly now because I kind of want to get this done, but I'm trying to explain things as I go. Hopefully this is at least a little bit interesting to some of you. Okay, so let's go on one more detour quickly and actually make sure that the kernels get this particle store thingy added here. So code gen test, that's the old one. That's the first particle system node graph that I ever got running, which just prints the action texts and then exits. And we can see here the stuff that actually has been added since yesterday. So now we have this business here. We have an allocator, Merlin effect pointer, we have the particle store because I just added it there by hand, current particle index, particle map, and can emit particles as a boolean, and there's some business there. But now if we actually regenerate that thing, it's gonna lose some of that stuff, right? So we go here, we open the code gen test, and we can copy like just the kernel at the end. Actually, we don't even need to copy it. We can just see it here. It has the particle buckets and particle bucket count, which we don't want. Those now live in the particle store. So instead, we want to have this line here. And that's quite easy to actually change. We're gonna want to go into Merlin native code gen context and just add it here. No more particle buckets. No more particle bucket count. Instead we have the particle store there instead. Like so. And now if we look at the generated stuff, now we have the particle store. Cool. It's just basically pieces of code that the system some sort of semi-intelligently puts together according to some logic. Okay, now finally we can turn our attention to this emit particle node again. So I think this is the this is the repeating logic business that I copy pasted this update function from. So we almost certainly don't want to do any of this. Instead we want to look at the C++ version of it. Emit particle node was here. So we've done essentially like this piece here. We've asserted that we are actually coming from the input pin, and if we can't emit particles, then we just return stop. Okay, so the next thing now then is to allocate this freaking particle index. So let's do that. Const particle index self kernel. What did we call it? We called it particle store allocate particle. So look at that. Right. Okay. So the next thing now we need is a world matrix, and oh my god, we don't have that. How unfortunate. So we can't get further than this line without going on a detour again. But hey, that is this stream. Today is one of those streams. So we're gonna have to get a world matrix from somewhere. The effect instance, of course, is the thing that lives on the C++ side, and it has a world matrix which is a 4x3 matrix. Again, we have a 4x3 matrix on Zig, on the Zig side, but it is it's not here in this solution, if you want to call it a solution. Let's see. Right, so I'm keeping these now as extern structs. If we go and have a look here on the game side, where we actually do have the matrix 4x3, this is just a struct, and it has these members here. I'm keeping these now as extern structs, and having all the functions just outside of it, to have this just be pure old POD, plain old data type here on the Sprinter side. So let's create a matrix 4x3 Zig here. I think we're gonna want to have those, so let's add them there as well. And we have pub_const matrix 4x3 extern struct. And some of you might be going like, hey, why are you not using the vector types from Zig? And yeah, I probably should at some point. They're sort of like in a little bit of a flux, and there's some rumors about some upcoming matrix types. I think I'm gonna let them settle for a little bit, and then I'm gonna convert at least, or at least add support for them. But they're like SIMD types, which are really good for some things, but they kind of require you to get really good performance out of SIMD types. You kind of want to stay in SIMD land as long as possible. And I'm thinking that's just not gonna fly with a lot of these particle update things when we're going sort of across DLL boundaries and across programming languages even. So yeah, I'm not using them yet, maybe at some point. Let's see, what do we do with this world matrix? I bet we're gonna do some yeah, we're gonna transform the position here by it. Okay, cool. That's for the box emitter shape. Here we're just getting the position out of it. That's basically like those three. Same thing there. But yeah, that's fine. Okay. So extern struct, Coolio. How do we get this now then? So we need to get it from the effect instance, which lives on the C++ side, and to get to the C++ side, we can use bind a lot, which is my special binding system. We already used this to get to allocate the particle bucket. Now we can do get world matrix. I think is the name that we want to use, isn't it? Get world transform. Like so. CPP pointer. And yeah, I think I'm just gonna give it the pointer to. That's an extern struct, so it should be completely fine to pass a pointer to this guy across the boundary. So we're gonna do we are going to do matrix 4x3 pointer transform, something like that, right? So we're giving it a pointer, a writable pointer to one of those guys, not returning anything, and then the C++ side can just write the stuff in there and then return, basically. So let's run the generation here. 0 errors, 0 warnings. That's great. Merlin. Then we go to native node graph, blah blah blah. And here's the function that we want to implement on the C++ side. Probably want to call it effect instance get world transform, like so. I'm going to add it here to the list as well to actually be bound. Uint pointer. What? Oh right, that's not that anymore. It's one of those, isn't it? But that thing is found here. Doesn't match the function type. Oh, right. Yeah, we just wanna return the pointer. There we go. Okay, that's better. That's better. Right. So we get the effect instance like that, and then we have matrix 4x3, which is actually not the same kind of matrix 4x3. Unfortunately, I think that's a basis matrix 4x3. Yeah, we don't actually want that. It's closer to like this kind of matrix 4x3 that we actually want here. So what I'm thinking is that we might want to see generated class bindings. One of the easiest way to get this is actually to do like an interrupt matrix 4x3, which is an actual type that exists. Generate it with that instead. And then we have the interrupt matrix 4x3 here. Like so. And then we can do this matrix 4x3 world matrix. World matrix is fine. Effect instance, get world transform. Probably have a conversion function from that from interrupt to interrupt. To interrupt is what we want. Basic interrupt helpers. It's a private header though, so we can't include it like that, unfortunately. So I'm just gonna yank it out of there. Yank. So this would be transform to interrupt world matrix. That's a little bit of a hairy way to do this, but maybe this would actually work the best. I don't know. Right, and okay. I bet we don't actually know what this is here now, do we? Wouldn't that be annoying? Right, it doesn't know what that is. But for that to work, we should only have to include it, right? So. Oh, it is probably because this sits in the Merlin namespace. I bet that's the problem here. So if we get rid of that, it will... No. No. What, can you not have that? Maybe you can. So let's comment that out. See what the issue is here. Max particles. Oh, okay, so now we have those. These would be like in the Merlin namespace. Oh, so this is annoying. This is annoying. Merlin. And replace all. There we go. Cannot convert from blah blah blah. Okay, yeah. I have to move some of these outside of that. Yeah, that's a little annoying. That would probably be Merlin as well. Would it not? Come on, go back. Can't go back. Right. It's here though. Here's where we want to build this. Okay, so now that builds. Can we build the entire thing? I'm not sure. Probably not. No. Probably not. Mesh particle renderer, okay. Yeah, we still have some. Let's see if we can find all the places where this is forward declared. Yeah, here it is inside of the Merlin namespace, and that is probably why it breaks. Here it's no longer inside of it. And this is stuff that is like... I'm not sure this is like the best way to solve this issue, but it might have to be good enough for now. Now we can at least build this thing. So that's pretty great. We do have another issue though on the Zig side now, I bet. And that's the fact that we don't have this interop matrix 43. Well, we can always just call it that, right? Call this interop matrix 4x3. And just work directly with these things. It's not really how I want to work though. Might have to do a little bit of figuring out of how this thing is actually to be solved. Because these interop things are interop versions of like math types. They're pretty handy. They're used in the game code all over the place. So for example, we have a vector tree, which is just a normal Zig struct. But then we have interop vector tree, which is a, well, here it is on the C side, but we also have it on the Zig side. That's not Zig. I need to go down to find Zig. Even more. Here we go. So here it is on the Zig side, and we can see it's really just like a small container for these three components. No member functions or anything. And here we have the interop matrix 4x3 as well. So I do a little bit of like conversion between these types to be able to just use normal Zig types in the game code. Here though, I want to specifically like point to things living in C++ memory from Zig. So I'm gonna have to actually use directly these external struct types. Which is good, it's good for performance, but it works a little bit differently than how the main game is set up. And so that's why some of these conversions done by Bindelot, which I also use for the main game, they don't kind of don't like really match here necessarily. But what we can do is, even though this now says interop matrix 4x3, we can just go in here into the generated type and just go like, nah, that's not an interop matrix 4x3. It's actually a Merlin native. It's not even a Merlin native. It's a Sprinter, isn't it? Sprinter 4x3, something like this. So if we do pub const matrix 4x3 here, because we haven't actually even imported that thing ever anywhere. Like so, we do pub const matrix 4x3. So we just expose the type there directly. Like that. And yeah, we can go in here and we can do Sprinter . Sprinter like that. Bloop. And this would be actually Merlin native. Like so. That should now build. Yes, and it does. So yeah, it is what it is. Anyway, let's keep going for a bit further. So now we have the particle allocated. We wanna get the world transform from the C++ side. Okay, So let's do that. I'm gonna move that off to the side a little bit, and we're gonna do const world matrix is, and this is now, let's think about this. This would be fairly native bindings, function pointers, effect instance, get world transform. All right, we don't return anything actually. Yeah, that's true. We don't return anything actually. Instead we get the world matrix out of that. So how do we do this now? We do it with a var world matrix sprinter matrix 4x3. It's undefined. Like this, and then we pass the kernel effect pointer to it, and then we give it the address of the world matrix. There we go. There's the world matrix gotten for us. Cool. Now we get to some of the magic in this whole code generation business here. So color test. We're here, and we want to read what comes through this pin here, which is a renderer. I want to read through what comes through this pin here, which is a float, which has an inline value, which is this. So if we connect this to let's add a float node here, and we just connect that to that, you can see that the field actually goes away, because this thing is either driven from the pin or it comes from this inline value here, which is set to 4. So in this case, this is 4, the lifetime, and the other value comes from this mesh particle renderer thingy. Okay, so we're not doing the code generation yet. As you can remember, we're just writing this by hand, and then we're going to do the code generation later. So the lifetime, which is called total lifetime in the C++ version, so let's call it the same thing here, total lifetime. This would be 4, like so. This would be like an inline value. Whoop, inline value. Thank you very much, Visual Studio. That's the total lifetime. And then we have the renderer ID. Renderer ID. And this would now come from another node, the node with index 3, so the one that comes directly after this one. Node with index 3 is right here. When we do this guy, we would probably create a function for this, which would be called get renderer ID or something similar. So I'm gonna create it here. All right, and we need Merlin native renderer particle renderer ID, which returns 0 here and right to do. Right, like this. These are annoying. We can just maybe unused self. Anyway, and then in the code generation, we actually register this get renderer ID as the symbol, so that it actually knows to call this function to get that, right? But in the meantime, we can do self kernel node 3, and it's just hard coded here. Node 3 get renderer ID, and this is what the final generated code is going to look like. So we can actually generate code like this that like just hard-codedly gets this from node with ID 3 because we know beforehand that this thing is actually connected to node 3, which is here. So something like that. And then when we do the code generation, we instead of like putting this in here, we use one of those fragments that I spoke of. In the code generation framework, the fragment is then actually expanded into, you know, something like this. And we do the same thing with this one as well. The fragments also handle the inline values. Right here. So what's the next thing here then? Now we're done like that. We've gotten the total lifetime. We've gotten the renderer ID. We want to actually now write those to the particle. You can see here that we are actually like setting them directly on P, total lifetime, and P, renderer ID. So let's do that. I'm gonna get a pointer to the bucket here. So const bucket. Yeah, the interesting thing here, of course, is the fact that like you kind of don't want to use this particle index for anything ever. You kind of just want to use the bucket index and the index within bucket, right? You kind of just want like these guys. Which is of course a little stupid that we have like this particle index here. And then we're combining them and then we're splitting them back up. So that's stupid. Yeah, we're gonna want to actually probably have a think about how this thing should actually work. Should this be like a small struct that has these two values in them? Maybe it should. Anyway, let's do bucket is self kernel particle store bucket index. You can see it's a pointer to SOA particle bucket. It's fine. And then we have bucket lifetime, total lifetime, particle in bucket index, and that's an annoying name. I'm just going to call it. Well, I can't call it bucket particle index because that's already used. Let's just keep it as it is for now. I don't care. Let's do it like that. That's the inline value. Just get rid of that, actually. And same thing here. We don't want to actually just write it to a renderer ID freestanding constant, but instead do bucket dot renderer ID particle in bucket index, like so. Something like that. Right, so now we've actually done those two. Now we want to have state emitter shape. And what is the state emitter shape, you ask? Well, it is essentially the thing that we've selected here in this drop-down. It can be a point, a sphere, or a box. Of course, we don't know anything about that here in Zig. So what do? We probably do like a pub const emitter shape is an enum. Doesn't need a type. It can just be an enum, and it can be a point, sphere, and box like this. Code generation allows us to actually specify these kinds of like declarations here. That doesn't actually even need to be. That doesn't even need to be public. Now that I think of it, I don't think we even need this at all. We can just generate the code that we actually want here, right? So this is a, what was that? That was originally was a sphere, was it? Yeah, it was originally a sphere. And that means that we can actually just generate the code based on what we have, right? You can see some of these fields here changing. If it's a point, it's just a point. If it's a sphere, we have a radius. it's a box, we have a box size. Just undo all of that. Back to the beginning, and we can see it's a sphere with a radius of 3. So we can actually just have that, which is like this version, right? I'm just gonna add like a small little sphere. Sphere was selected, or sphere shape was selected. Yeah, we don't need to have a switch statement here. This is the beauty of doing code generation. You can just like inline everything. Probably more than I do. Okay, get random unit vector. That's the next thing that we don't have, and we also don't have get random float. So that's not great. We're gonna need to get these from somewhere. And I don't have that code in Zig. So I think we're gonna probably just like stub those out for now. So let's do like how do we do this? Random unit vector. This would probably be like something like sprinter math get random unit vector, right? And so let's create a math.zig file here. Probably gonna want to have the standard one, and then we're gonna want to have the sprinter declaration as well. Where's math? There's math. Sprinter. Let's import sprinter.zig, and here we would have like bobfn get random unit vector, which would return a sprinter vec3. And here I'm gonna do a panic on. Actually, I'm not gonna do a panic. I'm gonna do a sprinter assert d false. The first one is actually a source location false unimplemented for now, because like vec3. Thank you very much. It's sprinter vec3. So x is 0, y is 0, z is 0. This will clearly tell me what's wrong, and it will actually even let me go here by just clicking a button when I actually run into that. What was the other one? It was get random float. So that would be just an F32. Same thing here. Let's assert that we don't have anything, and then just return 0. I think we're gonna actually have to somehow like give it a floating point, or sorry, a random device or something like that. But like, let's not worry about that for now. That's random unit vector, and then we have the position. Now before that, actually, we have a vector length. Yeah. State sphere radius and random. So sphere radius, I think, is, yeah, this is always an inline value. You can see there's no pin here. So sphere radius is always 3 currently. That means that we can do const vector length is sprinter math. Oh, we don't have. Oh, right. Okay. Yeah, we need to do that as well. My bad. Let's put it right here before the vectors. So math is import math.sig. Yeah, like so. Math get random float. Right, okay, it wants min max there on the C++ side, so let's do the same thing here. Min F32, max F32, and then some sort of random device. Let's quickly have a look here on the game side, where we actually have these things implemented. Math.zig, get random float. Yeah, here we go, okay. Yeah, that's what it's going to look like, so let's just copy that over directly. Stud random. Just closing things here. Yeah, I bet what we actually are going to want to do is something like this. Init new p rng. Yeah, but we need to get the random bytes from somewhere. Seed. Okay, what is this actually? This is a Soshiro something or other. Let's go to math. Yeah, it's here. Stud random default prng. Yeah, so what we might want to do here is actually create one in this node, right? So we would have a random device here. RNG is of type stud random default prng, and here in init we would do self.rng equals init, and then just give it something. What do we give it? Maybe it's a U64, so it's pretty handy. We can actually give it the kernel, and then we can give it the Merlin effect pointer as the seed, which is going to be somewhat random. And now we can actually give it the random. That would be self.rng. So that kind of worked out in the end, even though I didn't really have support for it yet. So the minimum is the sphere radius, and the maximum is... No, the minimum is 0, and the maximum is the sphere radius. The sphere radius, which currently always is 3, so that's like 3 and 3 decimal places. And I'm just gonna set here inline value again, just as a hint to myself when I read this code and I try to figure it out for the code generation, that like, okay, yeah, here in this place we actually gonna want to read the inline value from the data that is stored in the node, blah blah blah. Okay. Let's get rid of that. Alright, what do we have? What's the next step then? So now we've done that and that. We have position vec3. We're gonna get the translation from the matrix. I'm gonna do random unit vector times unit length. Add that to the vector. So, translation. This would be translation. That would be a sprinter vec3 where x is. I'm gonna quickly check here. It's 4-1, so this would be weld matrix 4-1. Y is weld matrix 4-2, and z rather is weld matrix 4-3. You can format it like that, maybe. So the position that we want to eventually calculate would be sprinter vec3 with a small v, and first one is translation, the second one is random unit vector. Actually, we want to multiply it by a float, so that would be sprinter vec3 multiply float. That would be random unit vector length. Right. So now all of this is used, and we want to actually put this into the bucket at the correct particle. So position for particle in bucket index. That is actually what we want to do. Right, I'm thinking this stream is gonna be all about implementing this particle emit node. We had so many pieces of boilerplate that we had to actually implement here before we were able to get anywhere with this thing. So I think I'm gonna implement this now in the form, without the code generation part, just this part. And I'm gonna call it a day, because this turned out to be way more complicated than I thought it was gonna be. So I think that's a pretty good place to call it quits for today. We are, however, almost done. What we need to do is we need to insert into the particle map, and then we need to store the current particle index, and then we need to exit via the particle pin. Luckily, this is like probably the most complicated node in the entire graph, because it just touches on so many different things. So cursor particle map, this has an insert function. We insert the cursor, which we get from the context cursor ID, and that is really just like the instruction pointer for the node graph, essentially. Almost like a virtual machine sort of thing. The particle is the particle index. So, and we can copy this handy little comment from there. And then we have another comment, which we'll also copy. We'll do self kernel current particle index is particle index. And finally, do context exit through pin. And this is another one of those things that we would actually generate with a fragment. Here we will go the exit pin. That's the particle pin. So that's really like the only one we have. So exit pin is like output pin dot particle. The destination node ID, we can actually look at it here. It's number 4. Number 4, and the destination node input pin index is that thing. Number 4, it's called in. So this is kind of stupid that we have to write this out. We don't actually have to write it out in the end. This stuff gets generated for us. That's the format, right? I'm just gonna make sure. Yeah. Yes, output pin. Then the node ID for the destination node. Then the destination node is like node.input pin dot whatever it is. So now we have the same thing here. Node 4 input pin and in. Cool. And this goes away. Okay, that was a lot. That was a lot. Of course, some of these things are just like got super complicated because we don't really have the math library in place here, because this is a completely new project. Also, we don't build currently. So what's the dealio? Missing field RNG. Oh, right. Yeah, we can just set that to undefined. It's not gonna There's really no way that can be used before init is called because it's generated code, so no one can accidentally call that. Well, I shouldn't say that, but it's extremely unlikely. So there we go. Now it builds again. Okay. This was a very somehow very chaotic stream. I apologize for that. In hindsight, I don't think this was very good stream material. What do you think? I think it was way too bleeding edge to actually do on stream. Probably not super enjoyable to watch, but hopefully it was at least a little bit interesting. This is the sort of stuff that I've been working on for the past few days. It's actually been going really well, considering I didn't really even have any of these things even remotely building or in particular running like a couple of days ago. But I think I'm gonna end the stream for today. If this is interesting, stay tuned. I'm gonna implement well, basically at least this thing here. My goal is to actually have the dust particles from the game actually running as native code in Pre-Alpha 3. Pre-Alpha 3, which is releasing as soon as I can get it out the door, basically. So like this particle effect here that you can see behind the car, I want to get that running in native code because it's the one that like hammers the frame rate the most, because you can have so many of it. Even just with one car, you can have just so many instances of that effect running, because you can hit the ground and then lift into the air and then hit the ground again and then jump into the air, and you can have like 20 of those running at the same time in just a single car if you're sort of unlucky, if you can call that unlucky, but still. And that's why it hammers the performance so much. But it doesn't run particularly well. So I want to get that. I'm gonna get that ported over to native code. In the process, make it so that we can eventually run all the particles in native mode. So that should be good. But yeah, do check back and stay tuned for more streams if this is interesting. Next time we look at stuff like this, it should be hopefully with a much more complete framework, so we can do some more sort of creative stuff on stream rather than just wondering what to do next. Anyway, that's all for today, folks. Do all the YouTube jazz, like and subscribe. Do check out Discord if you want to play the game. Pre-Alpha 3, as I said, is coming very soon. And wishlist the game on Steam if you want to help out the project. That's the easiest way to do that. It's just to wishlist the game on there. Other than that, have an excellent end of your weekend and a beginning of your week. See you next time.